Hi, welcome to Unit 23. In this unit, we're going to be talking about thermal radiation, basically radiation in the form of heat. I'm sorry about my cat, okay? So if you guys are hearing it. Anyway, so basically, we're going to talk about something, a model that physicists use to study this phenomenon called the blackbody radiation. And that helps us basically model the sun, or any star for that matter, or any object for that matter, okay? When it's hot, it's going to emit radiation, and that's basically the purpose of that model. Then we're going to explain, we're going to talk about the Kelvin temperature scale, the one that is used by astrophysicists because of the fact that it's more convenient than, for example, the centigrade or the Celsius system or the Fahrenheit, okay? And then we're going to talk about two important laws for astronomy, namely Stefan-Boltzmann law. And that law basically gives me, we can use it to measure the temperature of a star or an object in general without even touching it or going to it, okay? And that's based on the wavelength that is emitted, or the dominant wavelength, the main wavelength, the maximum wavelength, okay? Sorry, that's actually Wien's law. And also, how much energy is radiated per unit time, basically the power, and also emitted by that star based on its temperature. So there are two kind of it's a two process way of doing it. If I can find the maximum wavelength, I use Wien's law to find its temperature. Once I know its temperature, I know how much energy is emitted from that star, okay, per unit time. The third thing I can do is, if I see how bright the star is visually, or at least with a telescope, okay, the intensity of the radiation that I receive on the telescope versus how much it is actually bright, I use the inverse square law to find how far that star is. You see how this thing is all interconnected? We use basically astrophysics to measure a lot of properties of this object, of this stars, okay? It also tells me how big it is. Because if I know, for example, that this is supposed to be a red star, but yet it's super bright, like for example, Betelgeuse, then I know how big it is, because then it's emitting on a bigger scale than, for example, a blue star that is smaller, okay? That is dimmer to me. I don't see it as big as, for example, red star. Although a dimmer blue star is hotter than a bigger, larger red star, okay? So let's get going, okay? So again, a black body radiation is an idealization of objects that emit light, okay, or radiation in general. Think about this. You take a metal, a spoon, for example, and you put it on the oven. Hopefully you're not touching it directly, okay? You have some sort of a handle. That metal starts to glow, first of all, from kind of a low, kind of a, not that red, if you wish, dim red. Then it starts to redden. Then it becomes orangey. Then it becomes yellow. Then it becomes white. If it collects enough heat, and hopefully it doesn't melt on you. Okay, so that's basically the object that has a lot of energy in it, and it emits it in terms of radiation, in terms of a glow. That glow will change color depending on how much energy it really has, okay? So a black body is an object that if you shine light on it, it absorbs light no matter which frequency you have. So that's why it appears black. Had it been, for example, had it been, for example, rejecting the green, it would appear green because it accepts everything and rejects the green. You will see the green coming out, okay? In the same time, it's the same object that can emit in all frequencies too, okay? So it's a perfect emitter, perfect absorber. So that's an idealization, of course. There is no such a thing of a perfection. Well, when they studied this object, okay, they found a characteristic of that one. It's characteristic. It's going to emit in all wavelengths. from the very short wavelength, high frequencies, all the way to the long wavelength, low frequencies. Long wavelengths, low frequencies, yes, okay? In here, you will see, for example, the red curve in this diagram represents a low temperature device, okay? Like 4,000 Kelvin. So when I say low, it's still glowing. 4,000 Kelvin is a very high temperature, by the way, compared to everyday experience. Everyday experience, daily, right now it's about 300 Kelvin, okay? Room temperature is about 300 Kelvin. So 4,000 is more than 10,000, 10 times room temperature, so it's super hot, okay? 5,000, it starts to, the peak starts to shift toward shorter wavelength, okay? Meaning it's glowing in a different color. Here, it was red. Here, it's glowing in the yellow. At even higher temperature, 6,000 Kelvin, it glows in the blue region. So it's going to appear blue. However, because our eyes, it's going to peak around the blue. So it's not really going to appear blue. It's going to appear white. Why is that it's white? Because the entire spectrum is here. So from the red, there is a lot of red, albeit not as much as, for example, blue. And there is some violet also, albeit not as much as blue. But the combination of all of this will turn out to be white, because white is the combination of all of the entire spectrum. But if you are to put a filter around, you will see that it peaks around the blue in this case for about 6,000 Kelvin. Now, in terms of wavelengths, this peaks around 725 nanometers. 725 nanometers is about red. Okay, I know we said red is peaks at 700, so this is slightly longer than red. Okay, it's actually infrared. Okay, and then 580 is yellow. That's the peak frequency. And then 483, that is actually the blue. Okay, around 480 nanometers. Okay, so this is basically a characteristic of the black body. This is how black body behaves in the laboratory. Okay, you can clearly see in here that this, for example, orangey burner is hotter than this red burner, because its wavelength is peaking in the orange, whereas this one in the red. The red is longer wavelength than in orange light, so that's why this one is hotter than the other one. Okay, that's a phenomenon that we can experience on a daily basis, and that's what the physics behind it is. Okay, that's the same curve as we discussed earlier. So Wien's law in this case describes the peak frequency, how it changes with temperature. The higher the temperature, the shorter the wavelength. There is actually a numerical calculation in here between the two. And then Boltzmann law says that the curve, you see here the entire spectrum, if I add all of these frequencies and their intensities, and this area in here is the entire energy emitted, okay, throughout the spectrum as measured from the very short wavelength all the way to the longest wavelength. Obviously, it's less around 4,000 Kelvin, and it's far more than 5,000 Kelvin, and it's even more. This area in here encompasses this area and some. So that's what Boltzmann-Stefan law is saying, basically, is that the energy emitted depends on the temperature. The more the temperature, the more energy is. And that makes sense. The hotter the object, the more it's going to generate more energy, okay? Because it's built in and it's a lot of energy to emit that frequency. Now, I have been mentioning Kelvin and Kelvin a lot. That's a temperature scale that is used by astrophysicists and physicists also in astronomy. And that's a reference that you will see a lot in astronomy. And it's related actually to the Celsius scale by a shift of 273 Kelvin. And I mentioned earlier that room temperature is about 300 Kelvin, and that's because you have 273. That is the melting point of water, ice basically when it forms. Add to it room temperature, which is some 20 some odd temperature Celsius. So that gives us about 300 Kelvin in room temperature. So the difference between Kelvin and Celsius is just a shift of 273. That's why at 0 Kelvin, the temperature is negative 273 Kelvin. At 77 Kelvin, that's when nitrogen becomes liquid, it's negative 196 degrees Celsius. And then at 195, that's where dry ice, basically where carbon dioxide becomes solid, then that's negative 79 degrees Celsius. 0 degrees Celsius is 273. That's the melting point of ice, or the basically how when water turns into ice. So this is the temperature in Fahrenheit. That's 32 degrees Fahrenheit. Okay, so the Fahrenheit scale has two problems. First of all, it shifts things by the same amount. For example, the boiling temperature of water is 212 degrees Fahrenheit, which is 100 degrees Celsius, but it's 373, which is just 273 plus 100 for Kelvin. And in the same time, the melting point for water, it's at 32 degrees Fahrenheit, whereas it's 0 degrees Celsius, and it's 273 Kelvin. These two scales are linear. They grow with the same, basically, 1 Kelvin shift from 1 degree to another, from one level to another, is 1 degree Celsius. So they go one by one, like that, they scale like that. But the scale on the Fahrenheit scale is much finer. So 1 degree Celsius is not 1 degree Fahrenheit. As a matter of fact, there is a 9/5 ratio, okay? Almost two of that, okay? So that's the discrepancy in terms of Fahrenheit, for example, and Celsius. But in terms of Celsius and Kelvin, there is a 1-to-1 correspondence between the two. The only thing is you shift the starting point. At 0 degree Kelvin, or 0 Kelvin, I'm sorry, we don't say degree. At 0 Kelvin, theoretically, any gas will have 0 pressure. It doesn't make sense, okay? Or 0 volume if you maintain the pressure. Again, that makes sense. So what the point in here is that you can't reach that temperature. It's impossible to have 0 Kelvin. So if somebody tells you that I measured 0 Kelvin, they can't. It's impossible to do it in real life, okay? You can approach it, but you can never get into it. You can never get into it. You can get 0.0001 Kelvin, for example, but you can't get 0 Kelvin. So it's an absolute zero, which means that nothing can reach that temperature, which is negative 273 Kelvin. So if we go between interstellar space, for example, between the galaxies, or even between the stars, the temperature of that interstellar space or intergalactic space is about 2.73 Kelvin. So that's the lowest temperature in the universe on its own. In the lab, you can achieve colder temperatures than that, okay? But you can never get 0 Kelvin, okay? Or negative 273 degrees Celsius, or negative 460 degrees Fahrenheit. That's the absolute zero. That's hence the naming. As the temperature goes higher and higher, these two temperatures start to match, actually, between Kelvin and degrees Celsius, because of the fact that what's 273 versus 15 million? That's the core of the sun. So that's why it's negligible. There is still 273, but if you're going to add 273 or subtract 273 from 15 million, it doesn't matter. Okay, but there is a shift in here because of the way the scale changes, okay? That's why in Fahrenheit, that's about 27 million degrees Fahrenheit, which is the same thing as 15 million Kelvin or 15 million degrees Celsius. So that's just an idea of how these things scale. And on everyday experience, there is a big difference between these things, okay? But on a larger scale, they match one another, because at least these two. I mean, you're saying go towards 27 versus 15. 27 is 9/5 times 15, basically. It's just the scale. The shift is irrelevant in this case too, okay? So that's basically something about the temperature. So the point being in here in astronomy and astrophysics, really we use the Kelvin. But there is a conversion between these three scales. So if you're interested in trying to find it in degrees Celsius or in degree Fahrenheit, you can come back to this chart in here and it shows you how it's done, okay? And there are math formulas to do that too, okay? Again, I mentioned Wien's law, and Wien's law gives me the temperature in terms of the peak frequency, peak wavelength or frequency. Remember, there was another unit we talked about the wavelength and frequency are connected to one another. So in this case, it's expressed into lambda max. So there is a connection in here. If the peak frequency is measured in nanometers, which is typical, okay, then the temperature is 2.9 times 10 to the power 6 Kelvin nanometer per wavelength. Granted that that wavelength is nanometers, not in meters. So if it's in meters, then I have to divide by a billion. Okay, so this number in here changes from positive 6 to negative 3. Okay, And that gives me the shift, basically. That's why it's called the what is it? The displacement, the Venus displacement law, because it shifts basically the frequency shifts to the left in this case, because the wavelength, I'm sorry, shifts to the left. The frequency, if we're doing it, is going to shift to the right. Okay, so the wavelength shifts to the left in here. For a higher temperature, the wavelength is less. Okay, and for less wavelength, the temperature is higher, and that's what this thing is. Because when you divide by a small number, the ratio increases. Okay, when you divide by a big number, the fraction gets smaller. Okay? So that's basically the bottom line. And this temperature is very important to remember, that this temperature is not in degrees Celsius or Fahrenheit. It's Kelvin, period. That's why it's important to use Kelvin. Okay, because a lot of these laws, they're actually expressed in Kelvin. Okay, the next law is 2. This temperature here is also in Kelvin, but you have to raise it to the power 4, and that is this area in here under the curve. Okay, so in this case, we're talking about the amount of energy that is emitted per. So we're summing over the wavelength in here per unit time in this case. Okay, so it's going to be watts, the constant's watts per meter squared. So it's the amount of energy emitted per unit area. So it's going to be an intensity, basically, because the intensity is the amount of energy per unit area per unit time. And the energy per unit time is actually a power. It's in watts, just like your light bulb has 60 watts, for example. This one is expressed in terms of energy per unit time, and then also per unit area, per square meter. Okay. For the case of the sun, it emits 64 million watts per square meter. Okay. Remember, the sun is much bigger than a square meter. Okay. So you have to multiply by the area of the sun to find exactly how big that is. It's a huge number. Okay. And obviously, the sun's radius is what, 700,000 kilometers? Convert that to million meters, so it's going to be 700 million meters, and then square that number. It's going to be a big number, and then multiply it by 4 pi. That's the area of the sun. Then multiply it by this number to find how much energy is emitted by the sun every second, because that's watts. Okay. And this is this law. So this constant in here, sigma, that's the Greek letter sigma with a lowercase sigma, has a value of 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the power 4. So again, this temperature is in Kelvin. If I have 6,000 Kelvin, I have to take 6,000 to the power 4. That means multiply 6,000 by 6,000 by 6,000 by 6,000, 4 times, and then multiply it by this number to find the temperature, the energy emitted per unit area. So in the case of the sun's temperature is 5,800. So I'm to multiply 5,800 4 times by 10. So 5,800 times 5,800 times 5,800 times 5,800. And the result is going to be multiplied by 5.67 times 10 to the negative 8. Okay. And that's how we got this number for the sun. Okay. We know its temperature because we know its peak frequency. Its peak frequency is around the green. So we use the previous law to find its temperature. So if you use a spectrum and you see that the sun peaks around green, then you plug in this formula to find, first of all, since it's green, then you plug in this wavelength in here, you get its temperature, 5,800 Kelvin. You plug it into this expression and you find how much energy is emitted from the sun per unit time. That's basically the brightness, okay, how bright the sun is, okay? Or luminosity in this case, because brightness depends on the distance also from the sun. Again, this is the temperature, this is the facts about the sun, and the sun basically radius in almost all of the wavelengths, and that's why it appears white. It should be really, if somehow our eyes can see in a narrow region just like a filter, it will be green. But because our eyes see from the red all the way to the violet, so the entire spectrum is there. That's why the sun appears white. Thank you.